This video will walk you through the steps as to how to write polynomial functions given the zeros. Now, you'll notice that I'm going to correlate this here to the page in your note packet, the second half of section 5.6, titled Fundamental Theorem of Algebra. I will go over those examples here in a minute, but silly me forgot to include one of the easier examples I wanted to go through, which is here's some basic zeros that are some nice integers. How do we write a polynomial function in standard form using those? So I believe you have a blank side to the very back of your note packet. If you want to write one of these examples down here or just simply follow along, please go ahead and do so. So I'm going to go ahead and walk you through how to go and figure out, if I give you some basic zeros, how do we write a function? So let's say I give you the following zeros here. I tell you the zeros of the function are 1, 2, and let's go -4. Just picking a couple nice small numbers here. If those are my zeros, I can work backwards and turn those into factors. So a lot of this chapter, we've been taking little small factors here like x plus 8, x minus 7, finding the zero of them so we can do synthetic division or other stuff. If I give you the zero, I can work backwards and figure out what the factors should be. So keep in mind, 0, once again, as I've said 18 billion times, a 0 is an x-intercept, which means all of these numbers are equal to x. So technically, I've got three little equations. X equals 1, x equals 2, x equals -4. If I want to turn those into factors, what I'm essentially going to do here, and you don't necessarily have to show this type of workout, but what your brain should realize is, I want to get everything on one side. So theoretically, I'm going to subtract 1 and have x minus 1 as a factor. Subtract 2, have x minus 2. The third one, add 4, get x plus 4. All three of those things, if I set them equal to 0, those are my factors. So I'd have three factors of x minus 1, x minus 2, and x plus 4. Now, this is what I would essentially call intercept form when you have the factors all together, but we're going to write this in standard form, which means you're going to actually go ahead and, instead of how we've been spending the whole chapter basically factoring and ripping things apart, we're going to take all these factors and put them together. So the way that we do that is we simply multiply. Now, you really can't multiply three of these factors at once. You can really only do two at a time. Great thing about multiplying is it doesn't matter what order you do stuff in, as long as you do it consistently. So you can pick whatever two factors you want to multiply together. Just for the sake of organization, I'm going to go ahead and take the first two factors and multiply them. So that's where you do double distribution. So I'm going to have here, again, focusing on just those two together, x times x is x squared, x times -2 is -2x, -1 times x is -1x, and -1 times 2 is +2. Okay? So I have this big old factor here, and just so I don't forget about x plus 4, I'm just going to drag it down. Simplify your like terms. All of a sudden, I have x squared minus 3x plus 2, and I have x plus 4. Once I do that, I now all of a sudden have, instead of having three smaller pieces, I've got two pieces now. I've got two factors that I can multiply together. I'm going to go ahead and make sure everything gets distributed. So the x squared, the -3x, and the 2. So I'm going to have x squared times x is x to the cubed. X squared times 4 is 4x squared. -3x times x is -3x squared. -3x times 4 is -12x. Let's see here. 2 times x is 2x, and 2 times 4 is 8. Combine your like terms. You get a final standard form function of x cubed plus x squared minus 10x plus 8. So you can see, once again, it's using math that you already know. We're kind of going backwards from all the stuff that you've done in the chapter. If I give you the zeros, we turn them into factors. We figure out a way to multiply all the factors together. Key is, multiply two things at a time. All of a sudden, you end up with chunks of two sets of parentheses. It makes your multiplying a lot more organized and a lot easier to do. That's one of the easy ones to do, and I, again, use easy loosely because these are nothing but integers, okay? The math should not be that complex to get your factors. It's not hard to move your terms around. It's stuff you did back in Algebra 1. It's just that now you multiply three of them together. We're going to use this skill for the ones that you see in the notes, but they are a little bit more complicated because of the types of numbers that you're going to be dealing with. So there are two types of numbers we are going to mess with here. We're going to deal with what we call complex conjugates and irrational conjugates. Complex, dealing with those imaginary numbers, those i's. There's a very important bullet point that you'll see at the top of this page here. So oftentimes when giving a list of zeros, if you're dealing with complex numbers, typically in the list you'll only see one of the two that are given. So for example, and this is very important here, you might see in the list 3 plus 2i is a 0. What that also means, even though it might not be written, 3 minus 2i is also a 0. The reason why both of those have to exist is those are both derived from quadratic formula. Quadratic formula, you get that pesky plus minus sign, which means you're going to have two answers. If you have one of these two zeros given to you, you have to have the other with a switch of the sign. This is the same idea for what they call irrational conjugates, or in layman's terms, ones that involve numbers that have the square root symbol in them. So once again, let's say you see something like 11 minus square root 7. That means 11 plus square root 7 also has to exist. In most of these cases, they're both not going to be written for you. It's one of those things where you have to realize the quadratic formula and how you get these zeros because of what spits out. The only way you get these i's, you get these square root of 7 or whatever the case may be, it has to come from the quadratic formula. Quadratic formula has a plus minus sign, which means it doesn't matter if it only lists the positive or the negative version. The opposite one also has to exist as well. So we're going to look at these two examples here. Make sure that we have the right list of zeros, and we are going to figure out what equations we should write. So again, it's going to be the same type of math, but now we've got these more complex versions here. Complex as in more difficult, but complex with the imaginaries, irrational with your numbers with radicals. And we're going to go ahead and figure out what these functions should look like. So, biggest thing about these here is you're going to see there's more terms to multiply. You're going to have the same amount of groupings, but you're going to see more terms involved. You'll see what I'm talking about here in a second. So let's take a look here at these two examples. So we'll start with number 3. So we'll write a function. So there's a lot of verbiage here, but basically you're going to go ahead and do exactly what I showed you in the first problem. All you're going to worry about are the zeros and turn them into factors so we can go multiply. They'll have a leading coefficient of 1. You won't have to worry about that. That's just notation here to make sure that to basically kind of keep all of your problems here the same. But we're not going to worry too much about that. At any rate, the zeros that are given to you, you're given 2 plus square root 5 and 3. 3 is a nice one. That's great. 2 plus root 5, a little bit grosser. If you see one with a root, here's what that means. Your zeros. So we have the 3. I'm going to write out this list here so it's a little bit nicer. 2 plus root 5. Since you have a 0 with a root, it also means you need one with the opposite sign in the middle. It also means you need one with 2 minus root 5. Okay? So, we're going to do the same thing that we did in the last problem. I'm going to take each of those. So I'm going to make x equal 3, x equal 2 plus square root 5, and x equal 2 minus square root 5. I'm going to set these up so that the x and the 0 that we're dealing with are both on the same side of the equal sign. So in the case of the first problem here, we just subtract 3. X minus 3 equals 0. Okay, so my first factor is going to be x minus 3. Great. My second factor, I've got two things I got to move. I got to subtract the 2 and subtract the square root of 5. So I'm going to have x minus 2 minus square root 5 equals 0. So my next factor will be x minus 2 minus square root 5. I can't combine the negative 2 and the negative square root 5 because they're not like terms. That's why it looks like that. So in the last one here, again, I'm going to move the 2 by subtraction. I got to move negative square root of 5 by addition. So I'm going to have x minus 2 plus root 5 equals 0. So my final factor will be x minus 2 plus the square root of 5. So, we still have 3 factors. But if you look at those last two, You can probably tell they're going to be a little bit grosser to multiply because instead of only having 2 terms in each of the sets of parentheses, there's 3 of them. It still is the same math. It's just that there's a lot more terms to mess with, which means it's a lot easier to make a mistake if you are not super duper careful. So here's what I'm going to do here. I know in the first problem, I grouped the first 2 terms together and multiplied. When we deal with the problems that have these conjugates, so I have, again, very similar looking factors here, if you will, I'm going to multiply them together. The reason being is you will see every time you do a problem like this, if you start with those, you will get several things to cancel as you go and multiply everything together, which will ultimately make your math a little bit easier at the end if you can get stuff to cancel out early rather than later. So I'm going to go ahead and drag down the x minus 3, but I'm going to go ahead and worry about all the stuff I'm going to multiply here. So I got to distribute the x, then negative 2, and my negative root 5. Okay, so 3 terms for each of those. We're going to have a total of 9 terms to put together here, so we got a lot. So let's start with the x. X times x is x squared. X times negative 2 is negative 2x. X times positive square root 5 is x square root 5. Now we start with the negative 2. Negative 2 times x is negative 2x. Negative 2 times negative 2 is a positive 4. Negative 2 times square root 5 is negative 2 square root 5. Now the last one here, it's negative square root 5. Negative square root 5 times x is negative x square root 5. Negative square root 5 times negative 2 is a positive 2 square root 5. Negative square root 5 times positive square root 5, negative, it would become square root 25, which we're just going to make 5. So we've got ourselves this really, really, really long factor. Lots of things. But if you look closely, several things are going to cancel. X square root 5, negative x square root 5 will cancel out. Negative 2 root 5, positive 2 root 5 will cancel out. When you do these problems that have these weird components, these irrational numbers, these complex numbers, those elements, if you do this correctly, will cancel out. What you'll end up with is a much nicer factor here. So the x minus 3 stays out front. We look at what's left here. We're going to combine all of our like terms. I have negative 2x and negative 2x, which make negative 4x. 4 and negative 5, which make negative 1. Look how much nicer that is. It was really gross to start, but all of a sudden it comes out to something that's really nice and normal looking. If you do these problems correctly, they will come out very clean. It's just that they start looking like a mess because you've got roots, you've got 3 terms by 3 terms, you've got i's. It's a lot to deal with. When you do this last part here, this should be a lot easier to distribute because you're not messing with roots or anything like that. So let's just go ahead and distribute. So we take the x to everything. So we'll have x cubed minus 4x squared minus 1x. Take the negative 3 to everything. Negative 3x squared, positive 12x, positive 3. We'll combine our like terms. Final function that we'll have, x cubed minus 7x squared plus 11x plus 3. Again, you can't do this problem accurately without recognizing that you have an irrational zero, aka something with a square root, so we have to make sure to list the opposite, the conjugate of it. So all we do is list the version of it with a sign changed in the middle. Once you do that, it's the same process as I showed you in the first problem. It's just a lot of terms, but a lot of the crap cancels out in the middle. Gets you a pretty nice answer here at the end. The last example at the bottom is the exact same thing, except instead of dealing with an irrational, we're going to deal with a complex, aka an imaginary number. So let's go ahead and take a look here at number 4. So we have here, again, right polynomial function, blah, blah, blah. Your 0 is given to your 8 and 2 plus I. So again, just to make it a little easier to read, we're going to list them out. So here's 8, 2 plus I. Since you're given an imaginary, we also have to list its conjugate. So instead of having just 2 plus I, that also means you have to have 2 minus I. That has to be included in your list as well. So I'm going to do the exact same thing we did in the last problem. Each of them has to equal x to start. So I'm going to go ahead and show that first. And then I'm going to go ahead and get everything crammed to one side on each of these little equations I just whipped up. So I'm going to subtract 8 in the first one, end up with x minus 8 equals 0. I'm going to go ahead and subtract 2 and I each side. So I'll have x minus 2 minus I equals 0 for the second one. The last one I'll have to subtract 2 but add I. So I'll have x minus 2 plus I equals 0. So these are my three factors: x minus 8, x minus 2 minus I, x minus 2 plus I. See, right there, if I left that sign there, I would have thrown this whole problem off and had a whole mess of terms that wouldn't have gone away. So, once again, if you're doing something that has an irrational or an imaginary component, put those together first. Again, you will see that things will cancel here as we go throughout it. So I'm going to carry down the x minus 8. And now we're going to go ahead, lots of multiplying. So we'll put the x with everything first and end up with x squared minus 2x. X squared minus 2x plus ix. Then we'll go ahead and put the negative 2 with everything. So we'll have negative 2x, positive 4, negative 2i. And then we'll put the negative I with everything. So we have negative ix again. Another I times x, negative ix. Negative I times negative 2 is positive 2i. Negative I times I, negative I squared. So now we're going to go through. Ix, negative ix, go away. Negative 2i, positive 2i, go away. One other thing, and again, I know it's been a little while since you've done this. I squared, if you recall, and you need to recall, is a fancy way to say negative 1. So if I have minus I squared, that'd be the same thing as minus negative 1, which is plus 1. So all of a sudden, I can rewrite this, x minus 8, and then I can combine some like terms. I'll have x squared minus 4x plus 5. Again, all the parts that have i's disappeared. So again, you get a nice looking function after all. It's just that the zeros are gross. It looks hard to start, but if you do it correctly, you'll get all the i's to cancel out, leaving you with nice normal looking terms. So then we go ahead and follow it up. Lots of distribution here at the end. We'll multiply the x to everything, so we'll start off with x cubed minus 4x squared plus 5x. Then we distribute the negative 8, so negative 8x squared plus 32x minus 40, which will give me a final equation of x cubed. Excuse me, once again, went a little too fast there. My apologies. X times negative 4x, that should have given me 4x squared as my second term, not negative 4x. My apologies there. So combine my x squareds, I should have negative 12x squared. Combine my x's, I have 37x. And then I have this negative 40 at the end. And that will give me my final function here, x cubed minus 12x squared plus 37x minus 40. So that's how you go ahead and write polynomial functions when you're given the zeros. Most of the time you're going to be dealing with, like the first example, really nice integers, but the ones that do exist with irrational numbers and imaginaries, it's not that it's any more different, it's just that there are a lot more terms and it's a lot messier if you're not organized with your work. So once again, it's just a matter of grouping things correctly and taking your time with the process. But again, that's how you find and write polynomial functions in standard form when you're given the zeros of the function.